All right, so what I wanted to do, my big kind of takeaway today was I wanted to give you some information on the Chapter 8 quiz, and I wanted to give you the opportunity to ask some questions to help you get ready for that quiz. Now, the Chapter 8 quiz is going to have 6 questions. The first is going to be a calculation. So I'm going to give you some kind of raw data. You need to be able to turn it into a percent or a molarity. So for example, I tell you that you've got 35 grams of potassium nitrate in 150 milliliters of solution. You need to be able to turn that into a molarity for me. Or I give you some other information, you need to turn that into a percent by mass for me. Should be pretty familiar with that, especially after the post lecture that's due tonight. We did a number of examples of those. And again, the post lecture that's due tonight has even more examples of that. And there are certainly more examples of that in the Chapter 8 homework. The second one is something that we've only talked about kind of in passing. We haven't actually done examples of. And so one of the things we're going to do today is a definitive example of this. Conversions of solution concentration. In particular, going from percent to molarity or molarity to percent. Again, we've kind of eaten around the edges of this one. We did a number of examples where we went from molarity to parts per million to molarity. We'll do some more definitive examples where instead of going parts per million, we go to percent by mass. The process is essentially the same. There's just maybe one little thing that we need to straighten out to do those successfully. The third type of question, something that was part of the post lectures, but not something that we talked about exclusively here. Bronsted theory of acids and bases, identifying acid and base from a chemical equation. If you don't recall, acids donate H plus ions, bases accept H plus ions. And so that's how we can tell them apart from each other. So again, if we have time, if that's something that we want to talk about, that's something we can talk about today. Once you kind of identify it, it's pretty easy to pick them out. You just have to know what you're looking for. Fourth one, something we did a lot of examples of, titration calculations. The fifth one, and actually the sixth one, the questions 5 and 6 talk about the same thing. It's a redox reaction, identifying the element oxidized, the element reduced, the oxidizing agent, and the reducing agent. So specifically, number 5 deals with the elements. Number 6 deals with the agents. And so this goes back to kind of a concept that we talked about at the very beginning of our redox part of chapter 8. Now, with this in play, what I want you to notice is what's not on this list. There is no solution stoichiometry. There is no net ionic equations. There are no redox balancing questions. Now, of the concepts in chapter 8, those 3 are probably the most difficult. And that's exactly why we're leaving them off of this quiz. Not because we have a lack of faith in your abilities, but more we have a lack of faith in the ability to do that in a timely fashion. You're going to have 40 minutes to do this quiz. If I had one of those kinds of questions on there, I'd probably have to give you an hour to do it. So you will not see them in the chapter 8 quiz. You will see them in 2 weeks on exam 3. In fact, you can pretty much blood bank guarantee that all 3 of those are going to be represented in some form or fashion on exam 3, especially given the kind of nature that our exams have taken where you've got that unlimited time. I tend to put an extra kind of question or so in there to kind of help me figure out who really knows what they're doing and who's looking up the answers on Google. So that is your breakdown of the chapter 8 quiz. Again, it's a daunting quiz on its own. Those 6 questions are not easy. But we have left off probably the most difficult concepts at the same time. Chapter 8 itself is just a really difficult chapter. There's a lot of pieces and parts to it. We've been in that mode for about 2 weeks now. So any questions about the breakdown of this quiz before we start taking on individual questions? All right, so let me talk just a little bit about what the quiz itself is going to look like. As you've seen before, you are going to need the equation sheet. You are probably going to want a periodic table. Both of those have been embedded into the instructions for the quiz itself. And as such, you should be able to, I've disabled the things that would prevent you from accessing those. So if you click on the link inside of the quiz to pull up the equation sheet, it should not kick you out of the quiz and tell you to start again. It should allow you to work all the way through it. You are given 40 minutes for the quiz itself. So that should be more than enough time to do these 5 types of problems, especially since 3 of the 6 questions are really identification. What is the acid? What is the base? What is the, what element is oxidized? What element is reduced? That kind of thing. I would strongly suggest that before you click on begin, get yourself organized, make sure that you've got your calculator set out, make sure that you've got something to write with to scratch down the calculations. It does give you the whiteboard, but I know the whiteboard's kind of difficult to use if you don't have a touch screen. So make sure that you've got all that stuff there kind of at your computer, at your workspace before you start. That way you're not constantly moving around trying to find stuff to write with, stuff to do, because all that stuff is the things that Proctorio goes, hold on a second. Why is she moving so much? So, make sure that you're organized before you get started. All right, with that in mind, since we have not talked about number 2 exclusively, before I get to your individual questions, I want to do an example of number 2, just so that you can kind of see what it looks like and can organize yourselves in the appropriate fashion. So let's do a relatively simple problem here. Determine the molarity of a 7.1% sodium hydroxide solution. Okay, this is the kind of question that you'd be asked on the quiz for number 2. Now, obviously, I can flip-flop this. I could ask you to determine the percent by mass of a 7.1 molar sodium hydroxide solution just as easy. And if that's a direction that you want to see an example, we can do that kind of an example next. The real key to these kinds of questions lies in your understanding of your definitions. And I will tell you, this is where most of you are going to make your mistakes, if you make mistakes, is going to be in forgetting what these definitions are or forgetting what they mean. So we have to go through, what does 7.1% mean? Well, what it means is that I have 7.1 grams of sodium hydroxide for every 100 grams of solution. And what does molarity mean? Well, molarity would be moles of NaOH over liters of solution. So those are the two worlds that I'm trying to bridge here. Now, the first part, that should be seen really straightforward. To go from grams to moles, I'm going to need molecular weight or molar mass. I just divide my grams by my molar mass, and I would get moles. Simple enough. Now, for grams of solution to liters of solution, I know that at least in one case, this is kind of easy because my solution is the same. I don't have the same unit, but I have the same substance in the denominator. Solution is in the denominator of my first fraction. Solution is in the denominator of the second fraction. So to that end, I don't need to change my material. I just need to change my unit. I need to go from grams to liters somehow. Now, to that end, there is a piece of information that we are missing to solve this problem. Can anybody think of what is missing or what would help us to go between grams and volume of a particular substance? I heard it. Anyone want to say it louder? Density. Okay. Density would tell us the relationship between the mass of the solution and the volume of the solution. Now, that particular information was not given to us. I left it out intentionally here because I wanted you to see why we need to use it. Because this is the place, again, where most people make the mistake, is in the misinterpretation of density. Can't tell you how many times I will tell you that on a written piece of paper, you will show me that the density means that I've got this many grams of sodium hydroxide for this many milliliters of sodium hydroxide. The density is referring to the solution, not the solute. So let's say that just for the sake of argument here, we're making up all the values anyway. Let's say that for the sake of argument here, our density here is 1.10 grams per milliliter. So from this perspective, I've got everything kind of in place that I want in place. I can solve this problem in one of two ways. I can either take my density, or excuse me, I can find each of these values individually, put them over each other, and solve it that way. If I do that, the process is simple enough. 7.1 grams of sodium hydroxide. I need to turn that grams of sodium hydroxide into moles. 1 mole of sodium hydroxide. Molar mass of sodium hydroxide is sodium 22.99 plus oxygen 16 plus 1.01 for hydrogen 40.00 grams of sodium hydroxide. 7.1 divided by 40 to two significant figures, 0.18 moles of sodium hydroxide. All right. I've got the first part taken care of. 100 grams of solution. Now I use my density. 1.10 grams of solution for every 1 milliliter of solution. And there are 1,000 milliliters in a liter. $100 divided by 1.10 divided by 1,000 to three significant figures, 0.0909 liters. So 90.9 milliliters, 0.0909 liters. For molarity, I would take the two and divide them by each other. 0.18 moles of sodium hydroxide over 0.0909 liters. And to two significant figures, I would get 2.0 molar sodium hydroxide. So that's one approach that we can take. Split it, find each piece of the ratio, divide them by each other, get the molarity. Since everything that we did was a unit conversion, however, we can take that and use it like we would any other dimensional analysis problem. So if I go about this from a standpoint of dimensional analysis, I can get the same direction in the same way just by smashing together all of the conversion factors along the way. So 40.00 grams of sodium hydroxide in 1 mole. .10 grams of solution in 1 milliliter. 1,000 milliliters in 1 liter. Notice that all that happened is that these flipped over because now the 100 grams is in the denominator instead of the numerator. But everything cancels. other than moles of sodium hydroxide in the numerator, liters in the denominator. 7.1 times 1.10 times 1,000 divided by 100 divided by 40 to two significant figures would still be 2.0 molar sodium hydroxide. Now, it is entirely possible. It is entirely possible that the two different methodologies might create small differences in that last significant figure. So for example, in the bottom, the way we did it first, the value was like 1.98 molar that rounded up to 2. Here it's 1.95 molar that rounds up to 2. It didn't make a difference in this case. It could, but the tolerances in the programming of the question should allow for those small differences and still allow you to be okay. All right, any questions about this one? All right, do we want to see a flipped example where we go the other way? Okay, let's do the exact flip then. Determine the percent mass of a 7.10 molar NaOH solution if its density is 1.15 grams per milliliter. Okay, so this time I'm not omitting anything. The only way that you can solve these kinds of problems is you have to have a density. But the way that we solve it is pretty much exactly the same. We have to know what we have. I've got 7.10 moles of sodium hydroxide in every 1 liter of solution. And I want to take it to grams of sodium hydroxide per 100 grams of solution, if possible. And if that's not possible, then what I can do is grams of sodium hydroxide per gram of solution, and then multiply that by 100%. That's the definition of percent by mass. So I have to meet one of these two criteria. Which one I meet doesn't truly matter, so long as one of them get met. Now, the process that we follow is going to be pretty much the same. We're going to use molar mass, molecular weight, to go from moles to grams. We're going to use density to go from liters of solution to grams of solution. And again, how we get there, again, really doesn't matter. We can break it apart and put it back together if that's the way we want to go. Or we can kind of do what we did the last time and string it together in a long series and see where that takes us. So if we take it apart and put it back together, 7.10 moles of sodium hydroxide, 1 mole of sodium hydroxide is, what did we say in the last one? 40.00 grams. 7.1 times 40 is 284 grams of sodium hydroxide. One liter of solution. Well, we're going to do the same kind of thing that we did in the last problem. We're not going to calculate liters of solution, but rather convert that to milliliters so that we can use the density. 1 liter is 1,000 milliliters, and every milliliter is 1.15 grams. And so if I follow that, I've got liters, I've got milliliters taken care of. I just need to convert it into grams. 1.15 times 1,000 is 1,150 grams of solution. Now, we could take these numbers and recalibrate them to this, but that's way more complicated than it needs to be. Basically, I'd have to figure out what number to divide each of them by to get it from 1150 to 100. I could do it. I could set up a proportionality. 284 grams over 1,150 grams is equal to X over 100 grams. I could do that. I'd end up with 284 times 100 over 1150. To 3 significant figures, that'd be 24.7 grams of NaOH, which would mean it's 24.7% NaOH. Like I said, I can do that. That would be one way to solve it out. Probably the way that most of us would think to go before then, though, would be to plug them here and go this route. 284 over 1150 times 100% would get us the same 24.7% NaOH. So that's the one approach. The one approach is the break it apart and put it back together approach. The other approach would be a dimensional analysis approach. And that one, very similarly to what we did in the previous example, we're going to try to get it into grams over grams and wipe it out. So in that scenario, pretty much exactly the same as we did in the previous one. 1 mole sodium hydroxide is 40.00 grams. And then we just flip these two fractions. 1 liter for 1,000 milliliters. 1 milliliter for 1.15 grams. Now, if you do this calculation, 7.1 multiplied by 40, not today, huh? Divided by 1,000, divided by 1.15. What you would get to 3 significant figures, my solar calculator is hating me right now, is 0.247. Now that's grams of sodium hydroxide in 1 gram of solution. If I multiply that by 100, I get the same 24.7% sodium hydroxide. So again, either way that we look at it, either way that we split it, we end up in exactly, or at least close to exactly the same place. It's just a matter of personal preference. And so even the proportionality, that's a perfectly viable way of doing percentages because it is a ratio of ratios. But not everybody's wired to think that way. I recognize that. And so that's why I try to give you multiple ways of doing each problem. Okay, now I've burned up most of our time with these examples. If we run back, is there anything that we want to talk about other than question 2 that we want to look at with our remaining 6-7 minutes? Yes. Okay. Yeah, that's a good one. That's one that was raised this morning as well. So, one thing that you should know, I am recording this one. I recorded the morning one as well. I've intentionally chosen different examples for you guys versus for them, so that if you want to, you can look at the other video and see what kinds of things were brought up there. That's just as a point of reference for you. So the question would be something along these lines. Determine the element oxidized, element reduced, oxidizing agent, and reducing agent. The following reaction. So let's just let's pick on we've got bromine reacting with iron 3 to make bromide ion and got that reversed. And so this is probably an easier example than the one I gave this morning, but I'm a little bit more pressed for time than I was this morning. So what you have to do in this is you have to be able to assign oxidation numbers. That is the hallmark, the key activity for this. If you can't assign the oxidation numbers, then you're going to have a hard time actually going about doing this and doing it right. So what we have to remember are our cardinal rules for assigning oxidation numbers. Remember, there are 2 pretty key ones. One, the sum of the oxidation numbers has to equal the charge on the ion or the molecule in total. And 2, there are certain elements that have the same oxidation number pretty much in all situations: fluorine, oxygen, and hydrogen. So if I put those 2 rules together, I get the majority of these kinds of problems solved. So the real key here is I have to be able to assign the oxidation numbers and kind of take it from there. So to that end, for the bromine, I've got bromine as an element with no charge. The oxidation state for the bromine is in fact 0. I've got iron 2 plus. In iron 2 plus, again, this is a monatomic ion. It's the only element that's present. A positive 2 charge would belong to it. For the bromide, -1 would be its oxidation state because that's also its charge. For the iron 3, +3 would be its oxidation state because that's also its charge. So again, this is probably a more simplistic example. If you want something that's a little bit more complicated, click to the last 10 minutes or so of the morning video. You'll find one where we had to do a little bit of algebra to determine the oxidation states for the elements. In that case, it was manganese. But I've got about 2 minutes to sum this up, so wanted to pick something a little bit easier to follow. What we have to identify, again, is the idea of a matched pair. I've got bromines in one match. I've got irons in another match. What is happening between these two matches to tell us what's happening as far as their charge is concerned? I can see that the bromine is going from a 0 to a -1 state. I can see that the iron is going from a +2 state to a +3 state. Now, how would I identify each of those? Well, bromine is getting more negative, which means it is gaining electrons. That is reduction. The iron is getting more positive, which means it lost an electron. That is oxidation. So from that perspective, I can start to put together some of my answers. The element that was oxidized was the iron. The element that was reduced was the bromine. Now, what about my oxidizing agent and reducing agent? Well, again, those come from the elements, or excuse me, from the reactants themselves. And so if bromine is being reduced as an atom, the reactant that contains that bromine is my oxidizing agent, which means that Br2, the bromine molecule, is my oxidizing agent. My reducing agent would be the reactant that contains that iron, which in this case would be the iron 2+ ion. If you give me incomplete answers there, so if you just put in bromine Br or iron Fe, that's not correct. The oxidizing agent and the reducing agent have to be reactants, which means they have to appear as they do in the reaction equation, which means the bromine has to be in its molecular form, the iron has to be in its ionic form with the correct charge. Absent that, can't give you any credit for it. If you have more questions between now and Wednesday, drop me an email, stop by one of my office hours, check out the other video. I do talk a little bit about acid-base theory in that one as well at the end. Again, about the last 15 minutes or so would be really important to you for those last two concepts. But otherwise, have a good afternoon.